So now let us talk about thermal endurance tests. Now thermal aging is straightforward. You apply elevated temperatures on a material and you see how it behaves, whether it is able to withstand those temperatures. These kinds of results are generally available from the suppliers, and the suppliers' data can be used in order to select the components for an insulation system. But what we have to remember is that the thermal aging data that we have for the materials cannot be used to establish the thermal endurance limits for an insulation system, because the presence of other materials will influence the reaction between two materials in close proximity to each other. So an insulation system has to be tested with in an entirety with all the different materials in conjunction. So when you are performing thermal endurance tests on an insulation system, the insulation system has to be modeled such that it models the entire apparatus, entire machine, or the sections of the machine with all the associated parts. Once you age the material to a certain temperature, after that what we would probably do is, in order to estimate its behavior as an insulating material, we will probably apply electrical stresses on the material. Again, a thermally aged material will be stressed with electrical stress, and that too at elevated levels, and we will see whether the material fails or not. So that would be the technique or the methodology adapted to understand whether an insulating material is able to withstand a particular thermal endurance. Now, when we talk about materials, we have to concern ourselves with thermal identification and the classification of the materials. So for every material, there is a thermal endurance graph. The thermal endurance graph tells us how much time can elapse before a material breaks down or fails because of elevated temperature. So when does the time to failure because of high temperatures, the time that can be withstood by the material is given from the thermal endurance graph. And this thermal endurance graph plots the time to failure against the reciprocal of absolute test temperature. So we have something called a temperature index of a material. This temperature index of a material is the temperature that it can withstand for a given time. So for example, generally it could be 20,000 hours. So let's say we are talking about a class 105 material. It means that if you talk about a material with a temperature index of 105, it means that that material will be able to withstand 105 degrees centigrade for 20,000 hours. Generally, this is 20,000 hours. It's laid out by the specifications. When we are comparing two different materials, we can talk about a relative temperature index. So we have the TI of the reference material. The candidate material will have a similar TI. So if this is 20,000 hours, this will also have to be estimated for 20,000 hours. And we will compare the relative TI compared to the accepted TI of the reference material. And that way we will be able to figure out whether this material can be used in the insulating system. So a class F or a class 155 material should have an average life of, average is important because again this is a stochastic process, so we cannot have a situation where something catastrophic will happen exactly at 20,000 hours of application. A class F or class 155 material should have an average life of 20,000 hours when operating at 155 degree centigrade. So this is from EE634, which gives us a thermal classification of rotating machine insulating materials. So we have a numerical classification, also a letter classification. They mean the same, but with the letter classification, you have to remember which letter corresponds to what temperature. So you need to remember that a class A material will withstand 105 degrees centigrade. A class H material will withstand 180 degrees centigrade. Whereas if you use the numerical classification, it's easy to correlate. A 105 class material will withstand 105 degrees centigrade. A 155 class material will withstand 155 degrees centigrade. So then there are various kinds of test standards for thermal stresses. Some examples are ANSI IEEE standard number 1, which gives us the recommended practice for temperature limits in the rating of electrical equipment and for the evaluation of electrical insulations. IEEE 98 is used for the preparation of test procedures for thermal evaluation of solid insulating material. IEEE 101 gives us the procedures for statistical analysis of thermal life test data. These are just some standards I have mentioned to give you an example of the kind of test we might be doing. After thermal endurance, there comes the question of electrical endurance. Electrical endurance test is, of course, voltage endurance test, which predicts the behavior of an insulated system under voltage stresses. This could be in stator winding, does not have to be in stator windings, whatever application we are talking about. Now, the voltage used is much lower than the short-term breakdown voltage. If you remember the voltage time characteristics related to a dielectric material, when you apply elevated voltages, breakdown is very short, but much lower voltages can cause breakdown over a long period of time. And with aging test, that is the kind of levels we are interested in. We are not thinking of transient over voltages, but we are talking about maybe constant voltages, which are not even over voltages, but maybe very much the normal voltage, or maybe slightly above the normal voltage. Under normal circumstances, at short time, we probably do not expect any kind of failure to happen. But so at that voltage, in a short time, we do not expect breakdown to happen. But over a long time, we do expect breakdown to happen. So that is the kinds of voltages we are looking at in electrical endurance tests. So the voltage used is much lower than the short time breakdown voltage. And this is applied again to insulation systems, because we know that even if the material is able to withstand that voltage, an insulation system with a combination of different materials may not be able to withstand. So this is only applied to the insulation systems and not to materials. And it is often compounded with high temperature, because whenever you have high stresses, you probably also have high currents, you also have high temperatures, and normally the temperature and the voltage kind of drive each other. So in this case, in electrical endurance, we are looking at lower voltages than the short-term breakdown voltage. We are applying this voltage for a long period of time. I mean, this voltage will be applied for a long period of time on the insulation system in practice, in the field, and it may cause breakdown. So to model that, we will use lower voltages, but voltages higher than the normal voltages. So it will be higher, but not as high as to cause short-term breakdown. Most voltage endurance tests are for low voltages, and for 1000 volts and above, if you need to do voltage endurance tests, these are proprietary in nature and we don't have much information about that. Then there are the thermal cycling tests, because we know that when you have thermal cycling, things that are different from high temperatures, elevated temperatures cause one kind of failure, but thermal cycling, quick cooling and heating, cause a different kind of failure mechanism, drives a different kind of failure mechanism. Because this does happen when the conductor carries different currents, and therefore the conductor temperature changes rapidly. Fatigue cracking can happen due to rapid expansion and contraction. So there are IEEE thermal cycling tests. For example, IEEE 1310 evaluates the ability to resist failure of bond between ground wall insulation and copper conductors. Then AC/DC current, so you can have full-size bars or coils floating on supports so that axial movement can be simulated. Then AC/DC current is circulated through each coil such that the temperature of the copper rises to the thermal class temperature of the insulation. So you go to high temperatures which are in the range of the thermal class of the insulation, because insulation is expected to withstand a certain temperature. Go to that and then keep it at that for about 45 minutes. After that, shut off the current, cool it by air to 40 degrees centigrade in 45 minutes. So you're bringing it down. So again heating, again cooling. So this kind of maybe 500 thermal cycles can be completed. And out of you don't test this on every bar, on every coil. you need at least 4 bars or 2 coils to establish a clear trend. Now, in this case, what is the pass-fail criteria? You have thermally cycled the bars. After you have done the cycling, what would happen to the bars to indicate that it has failed? You need diagnostic test. It will not pass or fail. You need diagnostic test to determine if deterioration has occurred. One test could be voltage endurance. You apply voltage, and if you see a sufficient decrease in the breakdown voltage, you decide what is sufficient, and I mean that will come from experience or for the standards, that is it sufficiently lowered to indicate that this kind of failure process has rendered the bar ineffective to be used in insulation. Or you might be looking for PG test to find out whether delamination has occurred. But then this kind of test is a destructive test, and it's an expensive test. It is done on full bars, so it will only be done in, not done at a very all the time. It will be done all the time, but not on many bars. So these are some of the important aging tests that we, accelerated aging tests that we perform. Apart from that, we must often do work with multi-factor stress test. As I already said, it is in practice, it is not one stress that is driving the failure process. Generally, you will have a couple of stresses. You will have at least 2 or more 3 stresses aiding each other. So you have a synergy between the stresses. One stress aids the other, that stress then drives the other, and they kind of aid each other in driving the material to failure. A multi-factor accelerated aging test is one in which 2 or more stresses factors are simultaneously or sequentially applied at higher levels than would happen in service. Accelerated tests are always at higher levels, and you sequentially might apply different kinds of stresses. Then there might be special tests like nuclear environment qualification tests. So whatever test you are doing, you might be required to do it in a more harsh environment. For example, stator windings used in motors of nuclear power plants have to be qualified for operation or in harsh or mild radiation environments. Some tests that we perform on switchgear are AC, dry routine, voltage test on control and auxiliary circuit, resistance of main circuit, dielectric tests like lightning impulse, switching impulse, AC, PD, artificial pollution. We will learn about these diagnostic tests, non-destructive tests later. RIV test, temperaturized test, short time voltage withstand current, etc. These are the 2 references that I have mainly used for my for this particular lecture.